So welcome back, everyone. Thank you for being here. More people will filter in inevitably. Thank you for your patience as we've skipped a couple weeks. I was sick, and then there was a hackathon last week, and a bunch of other stuff has been happening. So glad to get us back on track, and I will be more communicative if there's any other scheduling changes. So thank you for your patience in that regard. Today, I think we're going to get started on object-oriented programming, which is interesting because it's like a term I've always heard, but I didn't, I know like what an object is in code, but I really had no idea what object-oriented programming is. So I'm very interested and excited. So I'll be presenting both the introduction to this part of the book as well as chapter 12. And with that, I will share my screen. Cool. You should all see my screen. So I've got some slides, and then we'll probably go into R and mess around with a few objects ourselves and see what they look like. So to start with, the book notes that there are different types of objects. So unlike some other languages, R actually has multiple object-oriented programming systems, but the book is going to focus on three of them, which are S3, R6, and S4. Um, S3 is used throughout base R, so it's very common if you're using base R, functions. Um, and an issue with it is that it has some very common conventions, but these conventions are not always kind of hard and fast rules. And this can get you in trouble if you're trying to make sure that the object is consistent regardless. And so there are alternatives. One alternative is R6. R6 is meant to escape R's copy on modify semantics. So if you remember when we talked about copy on modifications previously, this doesn't work like that. Instead, this modifies in place. The book says this is primarily used for things where you've got data coming from outside of R, for instance, from API um, requests. So if you're downloading some data from the internet or doing something of that nature, R6 objects are useful. The book also says that it solves some problems that S3 and S4 objects has, but it does not have details on what those problems actually are. And then finally, S4 objects. So this is a more rigorous rewrite of an S3 object. And it requires a bit more work to get it kind of formally in place, but when it forces rigor, we get greater encapsulation. We'll discuss what that word means in just a second. And it's well suited for large systems that evolve over time. If that sounds familiar, that's because this is the primary object type often used by Bioconductor. So if you're here from that world, you probably want to pay close attention to the chapter on S4 objects. So I mentioned the word encapsulation, which I'll talk about in just a second, but there's also polymorphism. So polymorphism is an important feature of object-oriented programming. That means a function's interface is separate from its implementation. And what that means is that you can use the same function for different types of input and give different types of output. And this didn't make any sense to me when I read it, so it's easier just to go into R, which you should see, and just test it out yourself. So I've just got a little file here. I'm just playing around with some things. I loaded the diamonds data set from ggplot2. If we run a summary on that data set, we see that we get this view where we get each variable and we get some descriptive statistics for each of them. But then if we run it on a single column in that data frame, we see that we get a different view. So this case, this is I believe a factor. So you see that it's different looking, even though we've run the same function because we gave it a different kind of input, we get a different type of output. And indeed, if we do, oh, come on, mouse. I cannot type right now. Interesting. Well, don't know what's going on with my keyboard, but the important part is you get different types of outputs, and it can accommodate different kinds of inputs. So that's polymorphism. The other term, this term I mentioned before, encapsulation. Uh, and this means that users don't really have to worry about the details of an object. If you have the right type of object for a function, it should just pretty much work. So the idea there is that, like, if I have a function that takes a data frame, then it should just work on that data frame. If like all other things being equal. So um, the user should probably not have to worry about too much about like the actual structure of that object if it just works. And so there's some more terminology as well, which I'll go through real quick. There's a class, so this is the type of an object. So um, a class would be something like, according to the book, it defines what an object is, and then the class is also hierarchical, so something that's of, like, I think the example they give in the book is like a double is also numeric. So there's a hierarchy where it's numeric, and then it's also a double, so it inherits everything that's true of numeric will be true for a double, although it doesn't go the other way, so everything that's true of a double won't be true of a numeric class necessarily. But there can be a hierarchy. There can be several layers to it as well. It isn't just two layers. Um, and then, oh yes, more examples here. A generalized linear model inherits from a linear model, so those are both classes. And then an ordered factor, so that would be like an ordinal variable like low, medium, high, inherits from a regular factor. So a regular factor might be something like, I don't know, gender or race. It's not something that's ordered, but the ordered factor follows the same kind of definitions as the regular factor, as well as some additional ones for an ordered factor. That's kind of how the hierarchical nature of it works. There are methods. So a method is an implementation for a specific class. So when I run summary and I get different results depending on the type of an object, that is because the method is defined for each of those types of that object. And then fields finally are data stored in an object of that class. So if you have a certain class of object, you can store different data about it. And that's some basic terminology. The book then goes into two paradigms of object-oriented programming. So encapsulated object-oriented programming, which is where methods belong to objects or classes. And what this looks like, because that meant nothing to me when I read that. But the example it gives is a method. If you wanted to call a method for an object, it would look like this. So you would say like, here's my object dot method, and then give it whatever arguments you have. So that is fully encapsulated. That's, I don't know fully, but it is encapsulated. So everything that is relevant to the method is done by calling it like this. In contrast, there's functional object-oriented programming, and this is where the methods are generic functions, and this is what you're probably more used to when you're working in R. So you've got some function, you give it the name of the object, and then any relevant arguments. And this is called functional OOP. And the book this says we will learn more about the difference between these two and why it's important in future chapters. With that, we are done with the introduction. So any questions so far while I try and troubleshoot why I cannot type in RStudio? Let me just close it, reopen it. There we go. The book also notes at the end of the chapter that there is this package called Sloop that you can use, and Sloop is great for learning more about the object types that you're working through. So O-type will give you the type of object. So we just try like an integer. We see that that is just a base R type. It's just an integer. We can try diamonds. That is a data frame, which is an S3 object. And then you can try something like I downloaded some data from Curated Metagenomic Data, which is a bioconductor package. And we can see the O type of that. So right now, why is it saying base? Well, if we actually look at the object itself, right now, oh, needs to load a bunch of stuff. But right now it is a list of it is a list containing a tree summarize experiment, but if we actually call the tree summarize experiment itself, we see it's an S4 object. And I thought this was like not something the book said, but I thought was important to note is that you can have one type of object inside a different type of object. So in this case, we have a list, which is a base R object, and then inside it is an S4 object. Which is a little kind of mind-blowing to me. It just, it's like, whoa, okay, this could probably get pretty complicated if we wanted it to. And so the book says, if you're confused about, like what an object is, just use this O type to get more information about what type of object that you have. And it functions better than I think there is a function in base R, but this one is more consistent, the book says, in returning the actual type. So with that, if there are no questions, I don't see any questions in chat. I will switch to chapter 12. So chapter 12 is about base types. So these are types that are contained within R, but first the book says we need to distinguish between what is an object. We've used the word kind of just to mean anything in R that's in there, basically, that's not a function maybe, but um, base objects in R are actually coming from a separate programming language called S, and S was developed before object-oriented programming systems were implemented in R, and so a lot of it has kind of emerged organically over the years, and so we can see that there are objects, which includes both base objects and object-oriented objects. Man, am I going to be saying the word objects a lot. So how do we distinguish between these two objects? Well, the book says, you can use O-type from Sloop or is object. So interestingly, so if we say is dot object and we give it a vector, it will say false because this is a base object, and is dot object is going to tell you if it's an OO object, object-oriented object. Sloop is a bit better here. It's more informative in that it tells you that it's a base object. And then if you give it like a data frame, you see that is dot object will give you true and O type will give you S3. So this is an example of why you would use O type rather than is dot object. And we can see here that that this distinction between what a base object is and an S3 object or an object-oriented object. We can also see this another way. So one thing that is different between base and I'm just gonna call them OO objects, is that OO objects will have a class attribute. So we can see that if we go into R and type that, so we're asking for the attribute for this vector. What is the class of that vector? Well, there is no class, but if we look at empty cars, we see the class as a data frame because it is an S3 object of a defined class. You can use this function to find the classes of both S3 and S4 objects. So, we can try that on that curated metagenomic data variable or object that I downloaded. So we see that it is a tree summarize experiment. So it works for both S3 and S4. Interestingly, if we, you can see more information using Sloop again. So rather than using, that ATTR function, you can use S3 underscore class and see what that gives you. So it's still just a data frame, but if we give it something like a matrix, we can ask it, the base R will tell us that this is a matrix, which is a type of array. And then if we use S3 class, we see that it's a matrix with integers in there, with numeric integers in it. So we see a little bit more about the implicit classes that S3 and S4 systems will use for methods. And we'll learn more about S3 class in chapter 13. Going back to my slides. Yeah, this is what I was showing. We can, yeah, got a little ahead of myself. In terms of base types, while only OO objects have a class attribute, every object has a base type. So if we ask for the type of a vector 1 through 10, we see that is an integer, and the type of empty cars is a list. And base types are not an object-oriented programming system because functions for base types are written in C. The book doesn't give a lot of information about what that means, probably because they don't want you to have to, figure out what C does with objects. But the important part is that base types are not OOP. And they also note that only the R core team can create new types. And they have not done so since 2011, but when they did so, they only added 2 types that are not types that you really ever use in R. They're used for diagnosing problems. And then the last update of new types in R was a special type of S4 objects which were added in 2005. So looking at the base types, some of them will look familiar to you. For instance, vectors, which we've seen in chapter 3, and here is a list of some of those types. Functions, which we saw in chapter 6. Environments, which only has a single type, which is environment, which we saw in chapter 7. S4, which will be covered in chapter 15. Language components, which will be covered in chapter 18. And then there are rare types that you probably won't use all that often, including, external PTR, which I think is a pointer function, which in a different language once I had a whole heck of a problem due to a bug introduced by Microsoft on a pointer function once. So I did have to deal with pointer objects, but hopefully you don't have to do that in R, because that was an annoying day. But these probably won't come up too much. Although I'm curious if anyone has any experience with these rare types of objects. Uh, Hearing none, we'll keep going. So the book then notes that the numeric type is really has some challenges to it, and we need to be careful when we think about it and talk about it, because R uses numeric to mean three potentially different things. So in some places, it's an alias for the Debel type. So in those instances, as.numeric is identical to as.debel. And then another possible things in S3 and S4 systems, it's either an integer or a Debel. So we see an example here where we run that S3 class function on just the number 1, and we find that it's a Debel. But if we specify that we want it as an integer, now it's an integer, but it's still numeric in both cases. And then is.numeric tests for number behavior, but factors are integers but are not considered numbers for is.numeric. So if you have a factor and you ask for the type of it, it will tell you it's an integer, but then if you check is.numeric, it will return false. So even though it seems to be an integer, it is not numeric. Which is kind of mind-blowing to me to think about, especially because the factor given in this case was the letter X. So it's interesting that that's an integer to R. And with that, that's where chapter 12 ends.
I think
So, oh yeah, go ahead, Marcel.
what they do is they save the values as integers, and then they just, because the text takes up a lot more space, so
Right.
saving a bunch of text would not be efficient, so they convert to integer and just save the labels.
Okay, so when you say factor X, it's really converting it into like the number 1.
Right.
Okay. When it stores it. Got it. Um, thanks for that. With that, that's kind of where chapter 12 ends. Is a very short couple of chapters. So I will open the floor to any questions or discussion of uh, Introduction to Object-Oriented Programming or base types.
I was wondering if we could maybe talk about encapsulation again. Like, I think
Yeah.
I'm a little confused, like the difference between that and polymorphism. Like, so is it just a way to get polymorphism or something?
Does anyone have any thoughts on that? If not, I can try and give my definition. Um, so my understanding from the book is that polymorphism is more the idea that if you use the same function for a different type, it still works, but it can give a different type of output. So it's literally that the the type of the object determines how the function handles it. Whereas encapsulation is just the idea that uh, the user doesn't need to worry about the details of an object because it is encapsulated. So they are related to each other. So if your object is well encapsulated, then that means that even if you have a different type of object, polymorphism will give you like a relevant, it will be able to process it and give you a relevant output. So they are related to each other, but I guess they're different attributes in that way. I don't know if, not to put anyone on the spot, but Marcel or Levi might have a better answer in that because they're both more seasoned coders than I am.
Yeah, that example where you had the method for encapsulation, um,
The one where I
pretty
was looking at
relevant.
the different summaries.
It would have to be like object dot method. I think it was in the slides.
Oh yes, when I talked about encapsulated versus
Yeah,
functional.
right. So every object can have its own method. So you don't need to worry about like an overall structure or API for the method, right? Because it will just work. It's attached to the object as the way I see it. So it can have any arbitrary number of arguments and it should still work for the encapsulated OOP.
Okay. I think the phrase you used there where you said the method is attached to the object. So that would be an example of a very like encapsulated
Yeah, like I was thinking of
OOP.
Python,
Yeah,
like you get an object and then you can use its method similar to using the dot, right?
yeah.
And as long as you have that object, you can just look at all the methods that are available for the object and use it without having to worry about a separate function that has all that method. What I'm talking about are the generics. So
Yeah.
it's a separate function that should have a method for that object with the same argument signature.
Okay. So what I'm trying to let me try and like put that in a specific example. So I think in Python, like if you want to find the length of a string, you'll give it the name of your string object and you'll say dot length. And
Right.
whereas in R, I guess, I mean, usually you'll say like, I don't know, you'll use string length or whatever it's called from string R, and then you'll say, here's my object and here's some arguments for it. Would that be like an example of the difference?
Yeah, because the way R is doing it, it has a generic
Yeah.
that it looks at and then looks at the available methods and finds the method for your class. So it's not really
Right, but that's
part of the object per se.
that's what it is.
Is the object dot length syntax in Python just a form of encapsulated programming? It's something equivalent to ours S3 usage where you would where you could specify it would be class dot method in S3.
Yeah, I think R has both, right? The recommended way is to use the generic.
Right.
But you can use the encapsulated way of doing things.
I can, how would I do that?
Like you can do summary dot data frame on empty cars.
Oh,
Yeah. So you can do it that way, but summary empty cars is the recommended way
what happens if I give it, okay.
because
Oh, that's
be-
probably not.
if you use summary empty cars, then you don't have to worry about picking the right object,
Right,
the right method.
okay.
Although I guess in some situations, maybe it's safer to specify because it's a way of typing your object, like specifying, I'm assuming that empty cars must be a data frame.
So it might
So-
be a way if you're developing like a function of saying like catching if the object is not in the expected format. Or not the expected type of object rather. So like, for instance, if you were expecting a table, you could do summary.table, and if it wasn't, if it gave an error message, you would catch that, I guess is what you're saying, Levi.
Yeah, I've never actually done that, but it does seem like a way to specify the type of your object.
Yeah, I had no idea you could even do like summary.data frame.
Yeah, there's summary.lm. This is only in S3, in the S3 paradigm.
Okay. What happens if you give it an S4 object?
You get an error unless, well, another reason to use the generic is that, for example, BioC generics redefines generic functions like summary in order to work also on S4 objects.
Okay.
Well, to work specifically on bioconductor. Well, I guess it's to create a generic function that can dispatch both on S4 functions or on S4 on functions for S4 objects or for S3 objects. I don't know how BioC generics does that. Do you, Marcel?
I don't know off the top of my head.
Yeah, but that's why I think that's why that package exists, because otherwise, you know, for bioconductor users, summary will also work on like a DESeq2 object, which is an S4 class.
So, okay.
Yeah, for like as data frame, it sets a S4 generic for as data frame.
It does, yeah. Okay. And as.list it does as well.
Yeah, so these methods that are normally S3 would work with S4 objects.
Interesting. Okay. Yeah, it changes quite a bit of like the base R functions. Interesting. Okay. I guess it's one of those things that it works so well you just never think about it, which is probably why example of why it works. You don't have to think about it. That's encapsulation. The user doesn't have to think about it. Cool. With that, are there any other thoughts or questions, topics for discussion?
Yeah, thanks for the explanation. I think that was helpful to see. I think I've always seen like the BIOC like generics, but I didn't know like exactly what it was doing or like how it's being used. So yeah, thanks.
Same. It's just something that gets loaded while you're doing something else, right? So, cool. Well, this was a short chapter, so I'm gonna put myself back in the sign up for another one so that I don't, because I feel like I got off easy this week. But next week, It looks like Jackie signed up to present, and Jackie will be presenting chapter 13, which is S3 objects, which I am interested to learn more about. So thank you all so much for being here for this shorter session, but we're getting back in the swing of things, and talk to you all next week.
Thank you, Chloe. Take care.
Yeah, thank you.
Thank you.
Thanks.
Have a nice weekend.